Hello everyone, so this video is going to be covering the fourth lipids lecture, which is on phospholipids, sphingolipids, and arachidonic acid, or arachidonate. Now as you can see, I've drawn out this triacylglycerol here, and this triacylglycerol, or I'm just going to abbreviate TG if I have to refer to it again, the triacylglycerol is going to be what's making up all of our lipids. This is the main component of lipids. And pretty basic structure, you just have your glycerol backbone chain, which is really just 3 carbon atoms. And then we have our 3 fatty acid groups, or our acyl groups, coming off of each of the 3 carbons, which is how we get our triacyl. Now we can take the structure and change it so that we get our phospholipids and our sphingolipids up here. So for instance, if we take away this last fatty acid group here, this last acyl chain, and instead of a bunch of carbons and hydrogens, we give it first a phosphate group, and then we'll have an alcohol group of some sort. And remember, this isn't just simply an OH group popped onto the end of the phosphate. This might be an entire R group with, as long as it has that alcohol attached to that R group. That's all we really care about. But if we do this and we take this instead of a triacylglycerol, now this is how we get our phospholipid. So this is a phospholipid, this structure. Phospholipids have various effects throughout the body. So for example, I've written out 2 different phospholipids right here. There's phosphatidylinositol, which is a precursor for signaling molecules such as our GTP chain. And there's also dipalmitoyl phosphatidylcholine, and that's a component of lung surfactants, the main component of lung surfactant. And lung surfactant is going to be reducing surface tension within our lungs so that it's easier for our lungs to expand and contract without collapsing. So these are 2 examples of phospholipids, but this isn't all we can do with our triacylglyceride foundation that we're adjusting. We can keep our phosphate and our alcohol group, and we can get rid of this other acyl group up here, and we can extend our glycerol backbone so that it's not only 3 carbons now, but it becomes an entire nonpolar tail. So it's going to be a hydrophobic tail like this. And now this is how we get a sphingolipid. And sphingolipids are mostly relevant to our interest because of their metabolic products. This glycerol backbone with this hydrophobic tail is known as sphingosine. Now sphingosine breaks down into a multitude of products, and if there is a problem in this metabolism breakdown, then we can yield different disease states. So if we take sphingosine, and first we want to convert it to ceramide. And from ceramide we get a bunch of different products. So we can get sphingomyelin, we can get cerebrosides, and then from cerebrosides we can get even more products. So we can get what's known as sulfatides, and finally we can get globosides and gangliosides. And like I was saying, if we have a problem with our metabolism somewhere in the chain, we'll end up with a buildup of one of these products. So for instance, if we have a buildup of a ganglioside, that is, we're unable to metabolize gangliosides, we end up with a disease known as Tay-Sachs. Now if we have a buildup of sphingomyelin, we're unable to metabolize sphingomyelin, we're going to get Niemann-Pick disease. And finally, if we have a buildup of cerebrosides here, we're unable to either turn them into sulfatides or gangliosides and globosides. We'll end up with a disease known as Gaucher's disease, or Gaucher's. Now let's talk about arachidonate. Now you can see I've drawn out the structure of arachidonate here, and you don't actually have to memorize the structure, but it is useful when we're trying to visualize what's going on. So as you can see, arachidonate has these almost ring structures. All we'd have to do is bind these 2 carbons together to form a ring, here and here. And the ease of these ring structures is what allows us to use arachidonate as a precursor for eicosanoids. So all of these other molecules I'll be talking about right now are going to be eicosanoids. So arachidonate can immediately be turned into a leukotriene. but it can also be turned into a prostaglandin, specifically prostaglandin H2. And then finally, prostaglandins can be derived into thromboxanes or prostacyclins. And prostacyclins. Now, all of these different eicosanoids have different effects throughout the body. So for instance, leukotrienes are found to cause our inflammatory response in asthma. So the enzyme responsible for deriving leukotrienes is going to be lipooxygenase. And of course then, if we block the activity of lipooxygenase so that this reaction doesn't happen, we won't be producing leukotrienes, and then we won't have that asthmatic response. So there's actually a drug that does this, accolate, which is a drug specifically used as an asthma medication. So this will block the actual formation of leukotrienes in general, but a different way to go about this is instead of blocking the creation of it, we could actually just block the receptors for leukotriene that cause the inflammatory response. And this is actually how the drug Singulair works. It is not by blocking the formation of leukotrienes, but simply by blocking the receptors that would allow the inflammatory response to occur. Now what about these other eicosanoids we have here? Well, down here we're forming prostaglandins, and this is done by prostaglandin synthase. And actually, this is where aspirin and ibuprofen work, by blocking prostaglandin synthase. They're antagonists of prostaglandin synthase. So aspirin then will prevent prostacyclins and thromboxanes from being produced. For the production of prostacyclins, we have another pretty simply named enzyme. It's going to be prostacyclin synthase. Whereas for thromboxanes, we have thromboxane synthase. What's interesting about these two different kinds of eicosanoids is that they have opposite effects in the body. So prostacyclins are actually going to be responsible for increasing vasodilation, as well as decreasing platelet aggregation. I'm just going to abbreviate AGGR for aggregation. Whereas thromboxanes have the opposite effect. They will actually increase vasoconstriction, and they will also increase platelet aggregation. Now, at first glance, it doesn't make any sense that we have this drug aspirin here, which is acting on both prostacyclins and thromboxane synthesis. And you may have heard before, though, that aspirin is going to increase bleeding times. It's considered a blood thinner. So how does this work, though, that if we're inhibiting one of the molecules that's responsible for vasoconstriction and vasodilation, how do we end up with a net result of bleeding when we're on aspirin? Well, as it turns out, thromboxanes are specifically in platelets, whereas prostacyclins are going to be made in blood vessel walls. So what this means is that while aspirin will have its effect on both prostacyclins and thromboxanes, inhibiting their synthesis, and we'll have sort of a wash when it comes to vasodilation and vasoconstriction since we're inhibiting both at the same time, the prostacyclins, since they're made in blood vessel walls and they have cell nuclei, they can regenerate themselves and regenerate their effects, whereas platelets have to be derived because platelets are anuclear, they cannot divide on their own. So that means that the effect of aspirin on thromboxanes and their synthesis lasts much longer than it does on prostacyclins in its synthesis, meaning that we will inhibit thromboxane synthesis for longer because it takes longer for platelets to regenerate, while prostacyclins will already have regenerated and working their effects of vasodilation and decreasing platelet aggregation, which will then lead to bleeding. And that's why aspirin causes blood thinning, even though it has its effect on prostacyclins and thromboxanes.